Hello everyone, my name is Meng from Total E&P Research and Technology in Houston. Today, I will share with you our recent work on using distributed task-driven approach to solve stencil-based applications. This work is a collaborative effort with Raut from Stony Brook University, Jonathon Anderson at Rice University, and my colleague Mauricio Araya at Total. Here is the disclaimer and the copyright reservation from the Total Group. I will first talk about our target application, that is, what problem we are trying to solve. Then introduce the proposed solution and how it differs from traditional methods. After that, I'm going to show you our experimental results and conclude with some key findings. The problem that we target on are wave equation-based applications. As we know, wave equation is of great importance in the applications for geophysics explorations. However, they are computationally expensive, specifically the stencil-based algorithms, which are the most computationally intensive segment. Our goal is to keep finding better solutions to improve performance of stencil computation by utilizing emerging programming models and new hardware architectures. And in order to evaluate those new software and hardware approaches, we developed a proxy application suite, namely Minimod. Minimod implements seismic modeling with different approximations of the wave equations. It is easy to build and port to the state-of-the-art in programming models. More information about this benchmark suite could be found in our archive paper. In this work, we use Minimod as the software framework for our experiments and implement different programming model approaches as individual kernels. This allows us to provide relatively fair comparison between the new approach and the classical methods. Before diving into our new approach, let's think about the classical method for stencil-based application. The traditional approach to reduce the time to solution of explicit and implicit methods for numerical simulations is to parallelize the computing. For example, shared memory techniques such as OpenMP are used when the problem memory footprint fits into the main memory. However, when the problem size exceeds main memory, hybrid approaches becomes necessary to distribute workloads among computing nodes. This is widely known as MPI plus X, where a message-based runtime coordinates the communication of data among nodes, and X can be any intra-node programming models or extended to accelerators such as CUDA or HIP, solves the local problem. However, in the new era of exascale computing with heterogeneous hardware computers, the classical approaches encounter their limitations, such as scalability and performance issues caused by asynchronous communications. This motivates us to find alternative parallel approaches which could be compared against the classical MPI plus X paradigm on competitive grounds. Among all the emerging techniques, task-based programming systems has been recognized as a promising alternative for bringing higher level of parallelism. Some popular runtimes include Legend, Parsec, HPX, etc. In this work, we explore the task-driven approach, namely Legend plus X. Legend is a data-centric programming system developed by Stanford. It provides optimizations available for improving scalability and performance of the target application as well as GPU support. In order to evaluate the performance of Legend Plus X and to compare against the MPI Plus X within the same framework, we implement both approaches as individual kernels in our benchmark suite. Simply speaking, our implementation contains two levels of parallelism, legend tasks and OpenMP threads. First, the overall domain is split into blocks, and the legend runtime distributes this block among the legend tasks. Legend runtime then determines which tasks can run at the same time and schedules them for execution on the available processors. Within each task, the embedded OpenMP runtime are used to distribute iterations to threads. Now, I will show you the experiments we conducted to compare Legend Plus X with the classical MPI Plus X approach. As mentioned previously, from application point of view, the two approaches are implemented as individual kernels within the same framework. In this case, we are able to provide relatively fair comparison between them. And from hardware perspective, we performed experiments on two different computer systems. The Summit supercomputer at Oak Ridge Leadership Computing Facility and the newly introduced Okami cluster at the Stony Brook University. Each node of Summit has two sockets containing IBM Power 9 processors with 44 total CPU cores per node. On Okami cluster at Stony Brook University, it is a pre-production system containing the first deployment of the Fujitsu x64FX microprocessors outside of Japan. Each node of Okami includes one x64FX processor, which has 48 compute nodes and 32 GB of HBM2 memory. In our experiments, we compare between Legend Plus X and MPI Plus X on both weak scaling, which is to see how their performance varies with the number of computing nodes while fixing problem size per node, and strong scaling, which is to see how their performance varies with the number of computing nodes while fixing total problem size. Let's take a look at each of them. In the weak scaling analysis, we evaluate the performance of MPI Plus X and the Legend Plus X with a fixed grid size per node. In order to have a meaningful reference, we choose the size of the problems which is demanding enough to cause stress of all relevant system resources. We run the application on 1, 2, 4, up to 32 nodes. The results for the target application running on Summit is shown on the left-hand side table, and the results on Alchemy is shown on the right. The expectation with big scaling performance is that as long as more resources are deployed and the problem size increased proportionally, the parallel efficiency should remain the same or close to reference. As we can see, the results on Summit indeed show the expected behavior for both MPI Plus X and Legend Plus X. On Okami, the weak scaling results is solid up to 8 nodes. However, Legend Plus X is less promising with 16 nodes and could not complete in time on the 32 nodes case. One interesting observation through our experiments is that MPI Plus X and the Legend Plus X present different domain decomposition sensitivity. Domain decomposition refers to solve a problem of a single region by splitting it into smaller subdomains so as to distribute to parallel computing nodes, tasks, or processes. There are many ways to split the 3D global domain into a given number of blocks. For example, if we would like to decompose the oriental problem into 32 subdomains, we can divide it into 32 small regions along x direction, or divide it into 32 regions along y direction, or firstly divide it into 16 small regions along x direction, and then divide each smaller region into 2 along y direction. In our experiments, we evaluate different domain decomposition scenarios. This table shows us, for selected partition scenarios running on Summit's supercomputer, the sensitivity of MPI plus X and the legend plus H to how the domain is partitioned into blocks. It is interesting to notice that, in general, legend plus X is much more sensitive to the partition scheme than MPI plus X, with some configurations performing much better than others. This analysis is used in the strong scaling results that we are going to present next. The best partition scheme is selected for each grid size and number of nodes. Now let's have a look of the results of strong scaling. On the left-hand side is the raw throughput of MPI plus X and the legend plus X, showing the stencil-based application with a 1024 cubed grid size, and running on Summit and Okami respectively. And the strong scaling curve of speed up over one node is presented on the right-hand side plot, with the purple line shows the ideal scaling trend. As we can see, the performance of MPI plus X and Legend plus X are competitive on Summit, as shown in the blue curve and the orange curve here, especially with less than 8 nodes. For the 16-node case, since each rank or task is solving a 3D domain, the halo exchange among neighbors starts to dent the overall performance. However, on Okami, Legend plus X suffers a performance penalty, as presented in the red curve, for which future analysis is underway. We also evaluated strong scaling on a larger problem size, for example, with 2048 cubed grid, as shown in this plot. Again, left-hand side is the raw throughput of MPI plus X and the Legend plus S running on Summit, showing by the blue and the orange curves respectively, and the strong scaling curve of speed up over one node is presented on the right plot, with the green line showing the ideal scaling trend. In this case, the same patterns are observed, but the drop of 16-node case is less pronounced, since a much larger problem is being solved, giving more chances for computing and communication overlap. However, we are not able to run this case on Okami due to memory restriction. In summary, we implemented and experimented with the Legend plus X approach for stencil-based application. Even though this approach is relatively regular and therefore has less potential for improvement over MPI, it is promising that the task-based approach yields results comparable to the MPI approach in both raw performance and scalability. In particular, results are robust on the production system Summit supercomputer. On Okami, which is currently a pre-production system, there are some performance issues, particularly affecting Legend, that we'll address in our future work. Our future work also includes using GPUs to offload the most demanding computing sections and to explore combining GPU kernels with task-based parallelism at the node level, and to extending this approach, for example, implement the I/O task-based kernel to explore more benefits from tasks. Last but not least, we would like to thank Total E&P Research and Technology for the support and the permission to share this work, and the Stony Brook University for the access of computing resources. Thank you very much for your attention.